Okay, so electromagnetic induction is basically, Suman, I figured out how to see your messages, so you may message me whenever you want to. It's defined as the total number of magnetic field lines that pass through a given area. Okay, usually, basically, you guys need to remember that it is the product of magnetic field strength, which is B, and perpendicular, this is very important, perpendicular area A. So I just want you to focus on this word actually. So remember, this is a scalar quantity, and the SI units for this are Weber, which is written as WB. Now, this basically, the symbol for flux is like this, and basically formula would be B times A, and this formula that you see right now, it is only for a single turn. Okay, now the next thing they're going to ask you is, and that would be most, this is a commonly asked definition, where they're going to say define Tesla. Okay, so whenever this comes, just remember the formula first, that magnetic flux over area is magnetic field strength. So you would say that 1 Tesla is equal to 1 Weber per unit meter square. That's right, meter square, like that. 1 Weber per unit meter square. Okay, you can also write this as just a formula if you want to, but that's fine as well. Okay, so when basically magnetic field goes through an area, so suppose this is a coil, and the magnetic field is going through like this. So this is basically the magnetic field. This is the coil, and this is magnetic flux linkage. Basically, linkage means that it is being basically linked with the coil, it's passing through that. Okay, now, so let's define magnetic flux linkage as well. Okay. So magnetic flux linkage is defined as the magnetic flux that interacts or links through a coil of n turns. Usually the linkage is, the symbol we use is flux total equals to BA times N. So it's basically, some people just says ban, but that's fine. Because in this particular formula, you will find a couple of things. So this part of the formula basically is the flux, magnetic flux, and this is the number of turns. Okay, so when this happens, what we are actually looking at, we're saying that, okay, now there are many turns in the wire, like n number of turns, and the magnetic field is basically going through here, maybe like that. So it's interacting with the coil like that. That's B, and that, my friends, that is the area perpendicular that we're looking at. All right. Any questions? Please let me know. Rafe, is it clear? Gatika? Gatika, why are you so quiet today?
Sir, I'm tired.
Okay, you just came back from school then. Okay, so now suppose I just want to tell you what happens if something is not perpendicular. So suppose, oh crap, I hate this. Please wait a second. Let me just fix this. Display brightness, I want only light, thank you. No. Wait a second. Thank God I have the shapes back. So now suppose first magnetic fields are going like that, like this, and like this. Okay, wait a second, please. There's something I got to do. So here, so now suppose the wire is like this, which is 90 degrees, and then the wire could be placed like this, which is at a certain degree theta. Oh, that's right, theta, not 60. And suppose the wire is placed like this, which is 0 degrees really. Now the first one basically shows you the max linkage, because you guys need to remember that the flux linkage can be regarded as BA n sine theta. The sine theta is basically just um, if I just put 90 degrees into sine, so it will just give me BAN, right? This one here, if I do that, it will be BAN sine theta, and any value less than 90 is going to give you a smaller number altogether. And the last one is zero linkage. And zero linkage because when you add BAN and in sine theta you add 0, so since sine 0 is 0, so this whole becomes 0. So you guys need to remember that in this one, why it is 0, because in parallel there is no cutting. Cutting means that like crossing of magnetic field with the wire, like that. All right, just remember that. Okay, I hope that's clear. If you have any questions, please let me know.
Yeah, bro.
Yes, Hassan?
Sorry, sir, wrong class.
Ah, yes, of course. Go away then. Okay, now. Aman and Fatma, do you understand this?
Sir.
Okay. Hassan, Atiq. Okay. Suman. All right. Now, so let's move forward. Now, there was one scientist. He was named as Faraday, and he gave Faraday's law of electromagnetic induction. In this chapter, you will hear about him a lot because the whole chapter basically revolves around him somehow. Now, according to Faraday's law, it states that the rate of change of magnetic flux linkage is directly proportional to the EMF induced. Okay. Now, the most important word that you guys need to remember is the rate of change. Like this particular part of this definition is so important. The reason for that is that what you guys need to remember is that in order to basically induce EMF or current, you got to keep on changing the flux above. So what I mean by this is, for the definition perspective, it can be written as EMF is proportional to the rate. Rate basically means that you're dividing the change in flux over time. Is it clear, everybody? Now with him, There was another scientist who basically later on he gave his own law, which is basically Lenz's law. And Lenz's law basically improves what Faraday has said, because it states that the direction of induced EMF is always such that to oppose the change that produces it. Now, this is kind of a complex law, but we're going to learn what it means in a bit, okay? Now, think about this way. Suppose there was a coil like this, and this coil was basically connected to a meter, let's suppose an ammeter. I'll just copy this because I will be needing it a lot. And there was basically a magnet which was kept far away from this, north and south, and the magnet was stationary. Now, when the magnet was stationary, what Faraday observed was that the current in this was not induced. The current was just zero. Okay. Now, the current was zero even though the magnet was quite far away from this. The magnetic field could not reach it, or very little magnetic field. So we would say that the flux linkage was just almost zero. It was not there, right? Now what happened is that when the magnet, which was right here, really far away, started moving in this direction, so what he observed was that suddenly there was not only a deflection, there was a deflection in this in a particular direction, and now the current was not zero, right? So what he said initially, he said, we're going to write here, Faraday observed, number one, when there was no relative motion. Relative motion means that either the coil or the magnet is moving towards or away from each other between the coil and the magnet. No EMF was induced, like you see in the first one, right? Then he said that the faster the magnet moved, the greater the deflection was shown, which means because EMF is proportional to change in magnetic flux linkage over change in time. So smaller the time, greater the deflection, or the greater the EMF induced. Is it clear, everybody? Please let me know if you do not understand this. Okay.
So isn't this what Lenz had observed and not Faraday?
No. That's what Faraday has observed, right? I'll tell you what Lenz did. So, right now, if you look at it, when the magnet is moving towards the coil, the flux linkage is increasing. So, there is a change coming up. Do you guys understand this? Then he thought, okay, maybe. What if I put the magnet right beside the coil itself, and then when it became stationary, so he basically observed that again the deflection was 0, although the flux linkage was maximum. Maximum means that there was like completely the field was going through the coil, there was a lot of cutting, but now the flux linkage is maximum, but still there is no current, right? Okay, do you guys understand this? So then he then moved it away from the coil, and when he did, he realized so when it was moving away, although the flux linkage is now decreasing because it's moving away, there was a deflection seen on the other side. So he said that basically not only the speed matters, but also EMF is induced only when there is a change in flux per unit time. Do you understand this? So that's about Faraday. Is it clear, everyone? Yes, Asantik, I'll do it. Okay, now think about it this way. Okay, in 10 minutes, please rejoin. So if the magnet is stationary and the flux linkage is 0, so there is no current, right? If it starts to move towards the magnet, towards the coil, there would be a change in flux linkage that basically causes the current to move, right? Current to be induced. Even when you put the whole magnet right beside it or even inside and it stopped, there won't be any change in flux linkage, which means that there won't be any EMF induced. So when it is moving away, then only EMF is going to induce, because now there is some change happening. Is it clear, Hasanatik? Okay. Now, what Lenz observed was a different thing. Lenz observed that basically if the direction of motion is reversed, the deflection occurs in the opposite direction to oppose the change. Now that's very important. Now let me explain it through something from an analogy that I've developed. So, Aman, do you have best friends?
So can I just copy the last point?
Yes. Okay, I'll ask Aman then. Aman, do you have best friends? No? That's not fair. Fatma, do you have best friends? Fatma doesn't have best friends. What is happening to this world? Yes, Gatika, do you have best friends?
Yes, sir, I do.
Okay. Gatika, how many are there?
3.
3. Okay, that's the number I was looking for. So she has 3 friends, okay? And they're all best friends together. Suppose 3 friends, okay? Now, in the first case, look at this. So, Gatika and her friends are just chilling out. And there is one person they don't really like, okay? The odd person. If he doesn't go into their group, would it matter to them or no? If he doesn't interact, he doesn't do anything, would it matter to you, Gatika?
No, sir.
No, right? So if the magnet here just stays stationary, he's not bugging the coil, the coil has no current really. Okay? Now, one day what happens is that Gatika and her friends are chilling, and then this person basically approaches them because she wants to be friends with them as well. Right? Now, because these people do not like this girl, Gatika, what would you do to shoo her away? My question. Yes, Gatika. What do you say?
Sir, I don't know. It depends on the person and scenario.
But you will try to, repel her, right? Don't you want to try to repel her?
Yeah.
Of course. That's what basically the electrons are just like humans, When the magnet's north is approaching the coil, basically according to Lenz's law, the current moves in a direction such that to oppose this change, so what the current does is it creates its own north here, south here, which causes it to move, like it moves through the coil so that it can oppose this, because the only way to oppose a north approaching is to create your own north, so it repels. Do you understand? So, again, if that person is coming to your group, you don't want that person in, you would want to repel her. So, if the magnet's north is coming to the coil current will move in such a way such that to oppose that particular change, and the change is that north is coming towards that. Do you guys understand now? Okay. Now, sometimes what happens is that you're truly wrong about people, right? And somehow that person just becomes your friend as well. You accept her. And then Gatika, you become best friends. Now, she's in your group and there's no change happening. And if there's no change happening, then you don't need to oppose it, right? So it means no current will be there. Now she's stationary with him. Like just the magnet's like really close, the flux is maximum, you interact with that person or the magnet interacts with the coil all the time. But because there is no change happening, you don't need to oppose anything. So now current is zero. Do you understand?
Yes, sir.
Okay. Then in the last section, if you realize, so you guys are like now the best friends in the world, and suddenly that person tries to move away, leaving your group. And you don't want that clearly. So would you try to stop her or no?
Yes.
Okay. And because the north of the magnet is moving away, to stop the north, what will you do? You will create the current will flow in such a way that it needs to create a south here of its own so that to attract it back. Do you understand? And in that process, to create a south here, it needs to basically flow the current in the opposite direction so the north is created. Okay. All right. Now, so where was I? So, let everybody connect in a minute and then we're going to talk about it. So what I was saying was that the Faraday law really tells you that how current is induced. Okay, there has to be a change in magnetic flux per unit time. But the Lenz law basically tells you what will be the direction of that current. Because it will be the same direction as to oppose whatever change is happening. If it's moving towards the coil, it wants the coil to create something to repel the magnet. If the magnet is going away from the coil, it would want it to come back, which means it will just create something to attract it. Do you understand now? Both the laws and their differences. Ratika?
Yes, sir.
Kuman? Aman? Okay.
Yes, you got it.
Okay. So remember this analogy, it will help you in understanding that, okay, this is going to happen. Now, let's do one more thing and then we're going to, stop the class. And that would be, and you guys will tell me now, what if a magnet is allowed to fall through a coil? Okay. Now, they've shown you a coil. I'll copy this. I need 3 of these actually. Okay, fair enough. Let's move them here. Now, so there's a magnet. So when you make it fall through it, Oh, let's make it in a different color. North, south, so it's moving this way. And now when it is right through the coil, north, south, and it has left the coil. So due to the action of gravity, it's falling. So in the first part, the magnetic field is like this. In the second one, the magnetic field is basically like this. The second part, okay. So now check this out. If when the magnet is falling towards the coil, what would you expect to see? Would like magnet is falling like something like this, like you see from top to bottom. So what kind of, in the first one, what will be the pole that would be created on the top of the coil? What do you guys say?
North.
North and south here. Very good. So that would basically cause the current to go in this direction. So suppose the deflection is like this. In this one, what do you expect when it's going through the middle? Yes, Saman and Aman, your input is valuable. Basically, it will show you no current at all. The reason is that the magnetic field is not changing, it's constant. So there's no change happening. And what about the third one? What do you expect at the bottom?
North.
North, because it needs to tract it back, it's falling down. So that means the current now will be moving in the opposite direction, like this. Is it clear, everybody? Do you understand this? So whenever you need to induce current, you got to have some change in magnetic flux linkage. Without the change, there won't be any current. I hope that I made myself